Section 4.4, Indeterminate Forms and L'Hopital's Rule. So we start off with this new theorem that when f and g are differentiable and g prime is not 0 on an open interval I that contains a, except possibly at a, and we have that the limit of f and g are both 0, or the limit of f and g are both plus or minus infinity, then we have that the limit of f over g is equal to the limit of the derivatives, f prime over g prime. So that's pretty cool, and it's not really immediately clear why this would make sense. It's also not so easy to prove, so we're not going to prove it. Instead, we're just going to assume that it works via magic. Notice we have to be very careful, though. If we have a form that's not indeterminate, so if it's not 0 over 0 or infinity over infinity, then there really is no reason at all that L'Hopital should apply, so you cannot use it. Before we even do any other examples, how about we take a quick look back at this limit that we didn't prove before. Remember that we said that it was equal to 1, which should make sense because near 0 sine is almost the same as x if you look at it closely enough. So it makes sense that if you go close enough to 0, then it should be basically x over x equal to 1. But notice that this is indeterminate because sine of 0 is 0, x when you plug in 0 is 0, so it is of the form 0 over 0. So we can do L'Hopital and get that this limit is equal to the derivatives, which is cosine over 1. Plugging in 0 at that point gives you that it's the limit of cosine of 0, which is, sorry, it's the limit of cosine at 0, which is cosine of 0, which is 1. So L'Hopital is pretty useful, as you could see. If that was too quick for you, let's do a more fleshed out example. So let's try to find the limit of ln x over x minus 1 as x goes to 1. The first thing you have to do whenever you want to use L'Hopital's rule is make sure that you're even allowed to. So let's look at the limit of the numerator. Well, ln x as x goes to 1, you can just plug in 1 because it's continuous. So you get ln 1, which is 0. Okay, the denominator limit as x goes to 1 is also clearly going to be 0. It's a polynomial, so we can just plug in. So it looks like this is indeterminate of the form 0 over 0. So let's write that. Because it's 0 over 0, we can use L'Hopital. So by L'Hopital, we can rewrite the limit. So our limit, ln x over x minus 1, becomes the limit of the derivatives. So the derivative of ln x over the derivative of x minus 1. Okay, so that's just the limit of 1 over x over 1. So that's the limit of 1 over x. And at this point, we can plug in 1 because it's continuous in its domain. And we get that it equals 1. So you might be tempted to say at this point, okay, well, if it's 0 over 0, then 0 over 0 must be 1. But that's not true. Sometimes we're going to see limits that are of indeterminate form 0 over 0, where one of the, either the numerator or the denominator dominates. So we could end up with a limit that is non-existent in the form of infinity, or it could be a finite number like 1, or it could even just be 0. Let's do another example. We're going to see if we can use L'Hopital by taking the limit of the numerator and the denominator. So limit of e is infinity. And for the denominator, it's clearly also going to end up being infinity. So that means that we have indeterminate form of infinity over infinity. So we can use L'Hopital. So this limit becomes the limit of the derivatives. Remember that the derivative of e to the x is e to the x, derivative of x squared is 2x. At this point, we still don't know how to evaluate this limit. But notice, if you were to take the limit at the top, that's infinity. Limit at the bottom, also infinity. So you can do L'Hopital again, because this thing is still of the form infinity over infinity. It's still indeterminate. So we'll do L'Hopital a second time. We get that this limit now, e to the x over 2x, is equal to the limit of the derivatives of e to the x and 2x. So that's the limit of e to the x over 2. We're going to take the derivative, which is infinity. Let's try using L'Hopital on this limit. So for the numerator, notice we have ln x. As x goes to infinity, that goes to infinity. And for square root of x, as x goes to infinity, that goes to infinity. So both of these go to infinity as x goes to infinity. So we can use L'Hopital. Okay, so the derivative of ln x is 1 over x. The derivative of square root of x is 1 over 2 rad x, which is the same thing as half x to the minus 1/2. 1 over 2 rad x, same thing. So let's rewrite that. At this point, you could say, hey, if we're going to infinity over here and infinity over here, then this is still indeterminate. It's of the form 0 over 0 now. So we should be able to use L'Hopital again. And you can, but you shouldn't, because this is actually pretty easy to simplify. If we just simplify 1 over x over 1 over 2 rad x, that's the same thing as saying it's 2 rad x over x. And rad x over x is 1 over rad x. So this is the limit of 2 over rad x. As x gets to infinity, the denominator gets super big, so this number gets super small, so it goes to 0. Okay, let's look back at number 2. Notice this was in the form infinity over infinity, indeterminate. This one was also infinity over infinity, indeterminate. Notice this limit ended up becoming infinity. Our other limit ended up at 0. So just knowing what type of the form is, it doesn't really help you in calculating the limit. It only helps you in the sense that you can actually apply L'Hopital. You still need to be very careful looking at the limit, going through the steps to make sure that you get the correct limit. Let's try using L'Hopital for this one. So tangent of x minus x, that goes to 0 as x goes to 0. And x cubed also goes to 0 as x goes to 0. So let's use L'Hopital. We'll take the limit of tangent of x minus x over x cubed. Set that equal to the limit of the derivatives. So derivative of tangent is secant squared. Derivative of x is 1. Derivative of x cubed is 3x squared. Okay, we still don't know how to do this. However, if I plug in 0 on the bottom, I get 0. If I plug in 0 on the top, I get 1 over cosine squared, which is 1 over 1 at 0. So that's 1 minus 1, which is 0. So it's still 0 over 0. So we can do L'Hopital again. So we do. We get that this limit is, again, the limit of the derivatives. Derivative of secant is secant tangent. So if I'm taking the derivative of secant squared, the 2 hops out in front by the chain rule. I get 2 secant times the derivative secant tangent. So it's 2 secant secant tangent. So it's 2 secant squared times tangent. And derivative of minus 1 is 0. So then derivative of 3x squared is 6x. At this point, limit of a product is the product of the limits. So let's separate this out. We can pull out 2 6 is 1/3. We can separate the secant limit from the tangent limit because the secant limit is easy to evaluate. So we just multiply these two limits. So we get 1/3 times the limit of secant squared. Well, remember, that's 1 over cosine squared. Cosine of 0 is 1, so this limit is just 1 over 1, which is 1. So it's 1/3 times 1 times the limit of tangent of x over x. Okay, again, we do not know how to do this. However, if I plug in 0 over here, that's 0. If I plug in 0 over here, that's 0. So this is still indeterminate of the form 0 over 0. So I do L'Hopital again. I get 1/3 times the limit of these derivatives. Derivative of tangent is secant squared. Derivative of x is 1. And again, secant squared at 0 is just 1. So this is 1/3 times 1, which is 1/3. Let's try finding this limit now using L'Hopital. So we get that this limit, x approaches pi from the left of sine over 1 minus cosine is equal to the limit of the derivatives, cosine over sine. Okay, so as x approaches pi from the left, this should become minus infinity. However, this is actually totally wrong because we didn't do something very important first. We just used L'Hopital's rule, but we didn't check our limits. So if we do that, we see that sine of x definitely goes to 0 as x approaches pi from the left, but 1 minus cosine x approaches, well, cosine of pi is minus 1, so this is 1 minus minus 1, which is 2. So this thing approaches 2 as x approaches pi from the left. This is not indeterminate of the form 0 over 0 or infinity over infinity. It's of the form 0 over 2. So we cannot use L'Hopital. So this limit definitely does not equal minus infinity. That being said, notice we can just plug in. Both of these functions are continuous at pi. So we can just evaluate them at pi to get our limit. We don't even have to use L'Hopital. It's easier than that. So we get sine of pi over 1 minus cosine pi, which is equal to 0 over 1 minus minus 1, which is 0 over 2, which is 0. Notice that when you try using L'Hopital when you're not allowed to, it totally messes up and gives you the incorrect limit. So let's cross this out. The moral of the story is that you should not forget all of your old limit tricks. If functions are continuous, don't try to use L'Hopital, even though L'Hopital is so much more fun to use. You should just save it for situations where you actually need it. Okay, and notice in this case, it's in the L'Hopital section, but it's not a quotient. And we only have L'Hopital for quotients. So you might be tempted to just plug in 0 at this point. However, if you do that, you get 0 for this guy, and you get infinity for that guy. Or minus infinity, but still. So this is indeterminate of the form 0 times infinity. You might be saying, okay, that's just 0. But then again, how do you know it's not just infinity? Infinity is so big, maybe it eclipses 0. And there actually is a struggle going on here. It could be 0, it could be infinity, depending on the limit that you're taking. It could even be a finite number. Just like as before with our quotients, you can't just assume that infinity over infinity is going to be 0 or infinity or 1 or anything else. You can't assume that 0 times infinity will be anything until you actually go and do the limit. If you had something of the form infinity times infinity, well, that would be just huge. There's no possible way that could be small, like 0 or a finite number, because you've got two giant numbers you're multiplying. So yes, any limit of that kind is going to end up becoming infinity. That's not indeterminate. But this one is. So let's rewrite this a little bit. Maybe we can actually use L'Hopital. If we say x ln x is equal to a quotient. Well, it's the same as ln x divided by 1 over x. Dividing by 1 over x is the exact same thing as multiplying by x. Well, now we have ln x going to minus infinity. And we have 1 over x going to infinity as x approaches 0 from the right. So I think we're good to go now. That means that we have it indeterminate of the form infinity over infinity. So by L'Hopital, we can take this limit of x ln x. We can first rewrite it as a quotient. And then once it's a quotient, we can use L'Hopital. So derivative of ln x is 1 over x. Derivative of 1 over x, well, that's x to the minus 1. So it's minus x to the minus 2, aka minus 1 over x squared. Okay, so tons of stuff cancels. This is the same thing as x squared over x. And then we keep the minus. So that's just minus x. And now we can plug in 0 and get 0. Here's another indeterminate form that we have not seen yet. If we plug in 1, then we get 0. So this thing is getting very small in the denominator, which means it's going towards infinity. And then if we plug in 1 over here, again, it goes to 0. So it gets very small in the denominator, so we get a very big number when we divide by a small number. So this is indeterminate of the form infinity minus infinity. If this is a huge number, and this is still a big number but not as huge, then we should expect it to equal infinity. But let's say this number is bigger, then we should expect it to be maybe minus infinity. Or what if they're both about the same size? Then we would expect it to be 0. Or what if one is just slightly bigger than the other one? Then it could be a finite number. There's too many possibilities. Because infinity is not a number, it's just a way of describing growth, how big something is getting. It's impossible to compare two different infinities, at least for us right now, without actually going through and doing L'Hopital's rule. L'Hopital's rule can actually tell us when something eclipses something else. Like if we went back to, where is it? This example, we could see that when we took this limit, e to the x over x squared, we ended up with infinity. So that tells you that this e to the x is growing a lot faster than x squared, which we're going to see at some point is, well, we've already seen it basically from this, that it's true. E to the x is faster than pretty much any polynomial. Not pretty much, it is faster than every polynomial. It grows really big. Whereas if you look over here, we can see that square root of x grew faster than ln x and ended up eclipsing this thing and making this thing equal to 0 when you took the limit. So when we're looking at these limits and their indeterminate forms, we really have to do L'Hopital to see which function is going to end up growing faster and eclipsing the other one, or whether neither will. So let's take this limit. we want to do L'Hopital, so we need a quotient. We've got too many quotients at the moment. So how about we rewrite this as a single quotient by finding a common denominator. So we get x minus 1 minus ln x over x minus 1 times ln x. Okay, so it looks like this is now indeterminate, right? If we plug in 1, we get 1 minus 0, which is 0. And over here we get 1 minus 1, which is 0 times 0 is 0. So this is indeterminate of the form 0 over 0. So let's use L'Hopital. We take the derivative, and the top we get 1 minus 1 over x, because derivative of x minus 1 is 1, derivative of ln x is 1 over x. On the bottom, we have to use the product rule. So we get that's x minus 1 times 1 over x plus 1 times ln x. Okay, so now how about we get rid of these x's in the numerator and denominator over here and over here by multiplying the numerator and denominator by x over x. So we should get that this is x minus 1 over x minus 1 plus x ln x, because we multiply everything by x. Still don't know how to evaluate this, but fortunately, if I plug in 1 again, I get 0. If I plug in 1 over here, I get 0, and over here, I get 0. So this is 0 over 0. So I do L'Hopital again. Taking the derivative of the top, I just get 1. Taking the derivative of the bottom, I get 1 plus, I gotta use the product rule again. So that's x times 1 over x plus ln x. Okay, at this point, it looks like I can just plug in 1. So I get that this is the limit, as x approaches 1 from the right, of 1 over 2 plus ln x, which is just a half. Okay, let's do another one of these infinity minus infinity ones. Notice over here, as e to the x, as x goes to infinity, e to the x goes to infinity, and then this guy obviously goes to infinity, so this is another indeterminate of the form infinity minus infinity. So we need to use L'Hopital, but in order to use L'Hopital, we're going to have to get a single quotient. So let's look at e to the x minus x. Well, that's the same thing as the limit, as x goes to infinity, of x times e to the x over x minus 1. Right? We can just factor out x. If we factor out x over here, we end up with a quotient. I know that as x gets really big, this goes to infinity. I know that as x gets really big, something's going to happen to this guy. Well, over here, this goes to infinity, this goes to infinity, so e to the x over x is indeterminate of the form infinity over infinity. So we can use L'Hopital. If we do L'Hopital on this, the top gets the derivative becomes e to the x, the bottom becomes 1. So this limit would be the limit of e to the x, just the e to the x part, as x goes to infinity. So this goes to infinity, and this goes to infinity. So this becomes something like infinity times infinity, which, as we said, is really, really, really big. So this goes to infinity, because the limit of x is infinity, and the limit of e to the x over x minus 1 is infinity by L'Hopital. There are a few other indeterminate forms we have not discussed yet. So let me get a little more space. if we have 0 to the 0 power, remember that's undefined. Infinity to the 0 power, also undefined. 1 to the infinity, undefined. All of these are indeterminate forms, just like infinity over infinity, 0 over 0. We can have a plus minus, just like infinity minus infinity, and 0 times infinity, or infinity times 0. So all these are indeterminate. In this case, we can do natural logs or exponentials in order to try to move exponents around to try to evaluate these limits and then use L'Hopital. Note that 0 to the infinity is actually a limit that gets you 0. It's not indeterminate, this one. So we're not going to do any of those. But for the other ones, let's do a couple examples. So if we have 1 plus sine 4x to the cotangent x, as x goes to 0 from the right, notice you plug in 0 over here, you get 0. So this is 1 to the infinity indeterminate. It's this one. So in order to evaluate this, let's do a substitution. Let y equal 1 plus sine 4x to the cotangent. It's not much of a substitution, but it'll make it a little bit simpler to write everything out. We're going to take the natural log of y and evaluate that limit, because that'll allow us to move around the exponent. So 1 plus sine 4x to the cotangent x. So then we move the exponent in front, so we get cotangent x times ln of 1 plus sine 4x. Gotta love those laws of logarithms. Okay, cotangent is 1 over tangent, so this is now a quotient, which is exactly what we want because we love using L'Hopital. Let's look at this limit now. The limit of ln y is the limit of this whole mess that we just wrote, ln 1 plus sine 4x over tangent. So that's just the limit of the derivatives. Derivative of ln 1 plus sine 4x, well, that's 1 over sine 4x. Then we apply the chain rule and take the derivative of sine 4x, so that's 4 cosine 4x. Do the chain rule twice, actually. So we get 4 cosine 4x over 1 plus sine 4x for the derivative of ln of 1 plus sine 4x. Now the derivative of the denominator. Derivative of tangent is secant squared. Okay, so if I look at both of these guys, they're continuous at 0. Cosine of 4 times 0 is cosine of 0, so it's 1. So I get 4 over, this is 0, 4 over 1 over this thing. I plug in 0, 1 over cosine squared of 0, 1 over cosine of 0 squared is just 1. So it's 4 over 1 over 1, which is 4. So we did the limit of ln of what we wanted, but we didn't get the limit of what we actually wanted, which is 1 plus sine 4x to the cotangent. So we need to be a little bit tricky. This is the limit of y as we defined it. We got the limit of ln y, so we need to somehow insert an ln y in here. Well, we know that e to the ln cancels. So this is the same thing as e to the ln y. Well, that's wonderful. E is continuous, so I can pass through the limit. Limit jumps into there, and I get e to the limit of ln y, which is 4. Okay, lastly, let's do x to the x. Notice this is indeterminate of the form 0 to the 0 as x goes to 0 from the right. So if I want to evaluate this, I can write that this is the limit of x to the x, which is the limit of e to the ln x to the x, because e to the ln cancels. So now I have the freedom of jumping this exponent out, putting it right there. So I get that this is the limit of e to the x ln x. And remember that if I want to put this limit through, we did this limit as x goes to 0. That was our example 6. We got 0 for that. So this thing is e to the 0, which is 1.